Okay. I'm just gonna go really fast.
It's perfect.
It's a dimmer switch back there.
Perfect. If you make it any darker, we'll all fall asleep.
All right.
Thank you.
Okay. Everybody can see it, okay? If you're not, just pull up further. So today we're going to talk about kinematics. I kind of added an informal there, just in case somebody else looking at the slide know that we're not giving a class for academic purposes. As Jebediah probably found out that when you operate a robot, you probably don't need much of this math. So.
Okay, if somebody's having chatter, can you step outside? It's hard to hear. Sorry.
Anyway, so I have that slide here. Why do we study kinematics, right? So if you design a new robot, for example, you need to kind of check the workspace and singularity, all that kind of stuff, so you can figure out what part of the arms needs to be lengthened, shortened, things like that. I mean, you couldn't quite do that with the building it and then try to test it. I mean, all this stuff can actually be done through some sort of math. You don't need, you don't need all these prototyping actually to figure out what the workspace is of the robot and things like that. And for example, you have some joint limits on the motors, and that impacts the solutions. Another thing is that once you study kinematics, you can simulate the robot movement. It's kind of cool. You can show it off, and if you want to go into computer graphics, actually study robotics. One of the reasons you study robotics is actually to go into computer graphics, because you learn so much about transformations. There are no other classes that teach transformation other than computer graphic class. But if you go into robotics, all you do is transformations in grad school. So that will kind of motivate. But if you just want to run a robot, you buy a robot, you don't need all this math. So the fourth point that I have here is more complex motion can be planned. What I'm trying to say is that, for example, if you buy a robot, usually they have the teach mode. You just record the motions. So you have a path that plan. So you record the movement of the joints. Then you don't need to plan. You don't need to calculate what the motion is, because you just record the joints angles. Okay. So it's almost like use a graphic package. You want to do the simulation of joints, or like human movement. And then after you move the joints around and say, okay, this is the movement I want, and then you go in and basically smooth the curve. So this is all you do in most of the cases. But let's say, for example, you want to figure out whether the robot can go through a very narrow channel with your arm. Then you need to kind of figure out how to plan these motions. So it's also sometimes you have a sort of speed requirement, smoothness and things like that, and then you have to plan the motions. So the stuff that I'm covering today doesn't talk about that, because you need to go to one level higher, basically look at the Jacobian of the motions. We're going to talk about in advanced class, as Jebediah probably know. The fifth thing is about obstacle avoidance. I mean, that's talked a lot about in the literature. Another thing is about, if you have more than the degree of freedom you need for a robot, how would you control the robot? So that requires doing math. You can't just put some numbers there and hope that it works. So before we go on, you kind of have to, if you design something for pick and place and things like that, you need to kind of know how many joints do we need. And for that robot, for example, the Kuka robot has 6 degrees of freedom, but a lot of time people don't have the extra degree of freedom at the bottom, the end, because for welding purposes, you do not need to turn. You don't care whether it's this way or this way; it's all the same. So that you don't need a 6 degree of freedom; you need 5 degrees of freedom. So the planar robot, for example, if you just want to move a robot to any vector to x, y locations, then you just need 2 degrees of freedom. You don't need anything more than that. So for example, if you want to build a robot that draws, put a pen in it, just like a plotter. You don't need the extra degree freedom. But let's say if you want to draw, build a drawing robot that can, move the brush like Chinese drawing or watercolor, then you need more than 2 degrees, maybe 3, maybe 4, depends on what kind of movement you need. So, the second point I have here is that if you need to move a robot X and Y to a certain orientation, then you need 3 degree frame for sure. I mean, if you have 2 degree frame, the robot's gonna move there, but you can control the angle of attack. So you'll see it later. I mean, in the simulation and also the real thing. So, in this case, for example, you have to specify the location of this. You only need 2 degrees of freedoms. But I have 4 degrees of freedom here, so I can use the 1 extra degree of freedom to do obstacle avoidance, do all kind of other things. But we're not looking at it. We're not talking about that today. So you just pretend that the one joint is kind of like the 0 degree. So basically, you have sort of like a single link. Now, this is kind of like what I talk about, but in a graphic sense. So here, you see here, you have the 3 degree freedoms. Let me just kind of introduce notation so that we're consistent. Q1 is the angle measured from the ground to the first link. Q2 is measured from this link to this. Okay? So Q2 is not measured from the ground. It's a relative angle. So this is a very typical robotic notation. So if you have any questions, I can refer you to some literatures. So phi basically is the orientation, which is the angle that you make with the ground. That's the orientation angle. Now, as I said earlier, you need more than 3 degree of freedoms to really do a very complex motion, because let's say you have obstacle here, you want to see if you have only 2 degree of freedom for this link and plus a rotation at the end, this link might touch the obstacle. But if you have this broken to 2 degree of freedom, then you can basically move this joint around. Then you can avoid the obstacle and still achieve the same positions. So this is what they call a redundant manipulator. I don't think in real life you see a lot of redundant manipulator except human, because most robots you buy 6 degree freedom instead of 7 degree freedoms. But there are 7 degree freedoms out there. I mean, for more complex assembly work. So let's just define the Planar Kinematics real quick. For a given set of Q1, Q2, Q to the N, compute the configuration of the entire robot. So given these angles, you should be able to tell me where the N effector is. So we are mostly interested in N effector locations. N effector is wherever you do the pick and place. We usually don't care about where the links are and things like that unless you have obstacles. Okay? But in the real situation where you have a very tight workspace, you may have to run some software, call it RT or something like that, to figure out where you could, move around. And you may have some situation where certain angles are not very good for your robot, because that require a lot of torque to turn, because that position, that location, it's kind of like your arm, there's certain, the 90 degrees the best. If you try to lift something, if you have it like this, it's very hard to lift. And this is already studied in the literatures. There's a thing called ellipsoid that kind of tell you how much, how effective it is in a certain region. So the forward kinematic usually is very easy. The inverse kinematic is the harder one. The reason is because if you place an object here and say I want to get there, and you have a lot of joints, you have to kind of figure out how to get there. For humans, it's kind of easy because we have visual feedback, whatever training we have since we're little, so we'll be able to get there without even thinking about it. But this for for software, you have to kind of figure out what these joints are. And there are a lot of trigonometry in, problems. For example, you see it later, that you have to make certain decisions. Okay? So for the forward kinematic equations, it's pretty straightforward. It's just you take the link, the first link, times the cosine of the first angle plus the link, second link, times the cosine of the first joint and second joint, plus the L3, which is the cosine 1, 2, 3, which is the angle 1 plus 2 and plus 3. So I define here, you can kind of see. So when I say C1, 2, that means the cosine Q1 plus Q2, which is basically Q1 plus Q2, and then times the L, which is basically this length here. So if you see X, most of the time you see cosine instead of sine. The reason is because when you have the L, which is your link, this distance is L cosine theta. This distance is L sine theta. Okay? So you see that if you see a sign here in the X, then you have an error because you're not defining the angle correctly. Okay? So with these three equations, phi is the orientation, by the way, so you equal to Q1 plus Q2 plus Q3. Okay? So now, the forward kinematic is pretty easy. You just plug in the joint, and you give you all these angles. I mean, the angles plus the X and Y location. But now you want to solve the reverse problem. Given these on the left-hand side, you want to find the theta 1, theta 2, or Q1, Q2, and Q3. Then you go into, you have to solve it by some geometrical reasoning. Okay? So what we're going to do is basically, I want to show one presentation, I want to present one solution. There are many solutions out there. You can even use the fuzzy logic to do some of this neural net. So by all means, this is not the only way to do this kind of thing. Okay? If you want to use a neural net, then basically you fit in the X and Y and theta, and then you give the joints. Then you can basically figure out what the nonlinear mapping between the configuration space and joint space. Terminology, joint space means referring to these angles. Configuration space refers to the X, Y, and phi. So basically we have these two equations. If we just rearrange the equations, let me spell that. Can't quite see as you get older. And you put the L2 C12 and L2 sin12 S12 on this side. Then you can see that if you just square both sides and sum them up, you can get rid of the sum of the cosine 12 and sine 12. That's a trick to get rid of this term here. Okay, so using this identity that you learned from high school or college, whatever, then you should be able to get rid of this term here, which is the L2 squared. Okay, as you can see in the next slide here, I define this term as x prime. Okay. Sorry, go back. And then y prime equal to y minus L1 S1. Then I can basically rewrite that previous equation as x prime minus L3 C123 squared, and so on and so forth. Okay, just a basic substitution here. It's really not much there. And then after you square it out and then you rearrange the term, all you have is just a cosine 1 and sine 1 term on this side. And all these are basic constant that, x and y are given. L1 and L2 you can measure from your robot, and you can just move these guys around. And you have this form here. And there's an equation for this. You don't even need to know. I mean, just basically plug it in. That will give you Q1, which is in this form, gamma plus sigma times cosine. This is the arc cosine. Basically take the inverse of the cosine, and you just basically get a solution for Q1. And the sigma, it can be plus or minus 1. And that controls the configuration of the joints. So if sigma is positive, I'm not sure whether it's this one or this one. I have to go check the. But anyway, that gives you two different solutions to a problem. Okay, to a 3-degree freedom problem. And once you get that, you can basically calculate Q2 because once you know Q1. Yeah, once you know Q1, then you can basically take this length here and then basically do an L, this length here, you know, and then you basically multiply the cosine Q1 plus Q2. Then you can basically take this equation and find a Q2 for it. Okay. And then once you know Q2, then you can find Q3, which is phi minus Q2 Q1. I mean, I know it's a little bit dry, so I'm kind of go fast. For 3-degree freedom case, it's pretty straightforward. I mean, you give me x, y, and phi, you can basically calculate Q1 and Q2 and Q3, and all you have to decide is which configuration you want to choose. Whether this, so you got two possibilities that you have to choose. However, for a 4-degree freedom case, it's much harder because then Q1 can be not almost everything, but can be a range of things and still achieve the same. Okay, so in that case, you need optimization. I use a technique called steepest gradient descent to determine Q1 that optimize the performing index. I'll show you a little bit of details in the next slide. Once Q1 is known, then I can use the method for 3-degree freedom to obtain the rest of the joint angles. So basically, we get rid of one of the angles by making it as a one extra freedom in the optimization problem. So it's no different from, let's say you want to optimize a mechanical design, and you say what's the weight of this thing that can give you the strongest, stress or whatever strength. Then you just post that, performance index, which is basically the stress it can take, and then you just change your length. But you have to change it a certain way because you can have, for one-dimensional case, very easy. You just either go positive or negative. But when you have like a two parameters, then you have a space that you have to walk. And it depends on how you define the performance index. That's why a lot of problems that you solve in grad school is like optimization problem. Because you got more degree freedom that you can solve. So you need optimizations.
But without optimization, it'll still get to that where you want it to. Just maybe not the fastest.
I mean, without optimization, you can't solve the problem because you have too few equations.
Oh, okay.
It's kind of like saying that, x plus y equal to 10. What's the value of x and y?
Okay.
So it depends on whether it's a discrete problem or the real problem. If for the real number problem, you have infinite problems. For the discrete problem, depends on range. You have a set of Cartesian product between x and y that gives you the solution. So I mean, I'm just saying that you have to choose a solution. So when you choose a solution,
you need a strategy, basically.
Yes, exactly. Yeah, it's kind of like you got the sensor telling where the line is. You need to figure out where to go, right? There are thousands of ways of doing it. I mean, get to where. You can use the rules. You can do fuzzy logic. You can do neural net. You can do some sort of AI.
Pick a number.
Pick a number, random. It's also solutions. But the thing is that with the extra degree of freedom, it allows you to kind of figure out what kind of movement you want. Okay. So this system is derived from. Actually, I'm sorry. I jumped a little bit. I was supposed to give I might have this one, the older slides. I'm skipping 2 slides. That's okay. Let me just go to the. So with that, we can kind of look at. A demo for a 4-degree of freedom. So let me explain what's going on here. So this robot that I'm simulating right now. Supposed to trace a circle with a certain type of orientation. Green box basically tells you where the desired orientation is. So it's not a typical problem where you don't care how to get there. You also not that you care how it gets there. You also want to put it in a certain orientation. It's like maybe you need to do certain tasks around it. So here I'm simulating for different initial conditions, and then you spin around and then you jump to another initial condition because I'm checking whether there's any problem with my solutions. Without this, you sometimes get into some solutions that you get into not a number because of arctangent. These functions are very notorious. If you don't condition them well, you get very bad solutions. And there's certain kinematic solutions are better than the other because of calculation purposes. As you can see, sometimes it's not able to track this. The reason is because we have a joint limits on this thing because the robot cannot move 360. Let's say I say, okay, can you go from 180 degrees to 360? You can't do that. You cannot just you hit itself a lot of times unless you design a way that it doesn't hit it. There are robots that does that, for example, for the volumetrics. But in this robot that I have a joint limits of 30 degrees on each side. So basically I only have 300 degrees to work with. So that poses a problem. You see that sometimes instead of bending the arm a little more, you couldn't do it. You see, you lost that, you see? Then you try to switch it over, but it doesn't, because it's just math. It doesn't know that it's not supposed to spin over and hit itself and go around. So you see that it does that a lot. When you try to spin, when you get to here, you see? They're crossing each other. So that's just math, I mean, because when we pose the problem, we basically pose it as a math problem. So it doesn't have any kind of knowledge about you're not supposed to link, not supposed to cross each other, hit each other. And if you look closely, you see that you sometimes cannot catch that. And then you try to catch that in that case here. Earlier, you cannot quite do it.
Can you add those in as constraints in the model?
I already did.
Okay.
Yeah.
I mean, without a constraint, you got perfect solutions,
Right.
right? Because you get there, as long as in this workspace. It's just math, right? You got, let's say, 3 degree of freedom. You know where orientation, just math. You definitely get there because you get 3 degree of freedom. You have 3 joints, definitely you get there. The problem is that when you have joint limits, the solution you get may not be perfect. In order to search for the perfect one, you need to kind of move one at an angle, let it float, like become a free variables, and then adjust it. So this is actually doing some optimization here. You see here, it's doing all this calculation here, try to optimize the errors. The error criteria here I'm using, for some reason I don't have that slide. I have it on the latest version, so let me see if I can redo this part here real quick here. I'm sorry. Yeah, see in this version I have the equations here, and basically I'm optimized. This is the steeper descent that I'm using that allow me to modify the joint, first joint, based on the gradients. Okay, and this is the step size. I'm using a constant step size to move my joints around, and then this is the cost function is trying to optimize. There's some weighting on this thing, so you can weight it. So you can say, I don't care about the orientation. That's what I did basically. I don't care much about the orientation. I just want it to be. You see it later. Sometimes you don't care about orientation, even though I specify certain orientation. So this hand-eye system is basically based on a CMU 3 degree of freedom hand-eye systems. I changed certain things in there and use a different type of Logitech camera. You can go online basically find out about this. You just type in hand-eye systems. let me give you a overall what the system's doing. Basically, you have a vision systems that give me where the location of the object. I'm tracking, by the way, I'm tracking this red object here. And then the path planner will basically give me the joints based on the joint limits and all the optimization we just talked about. And that would fit into the control system. The control system basically try to drive the robot to the desired locations. So there's some little bit technical details here. I got a vision system running at the 50 Hertz, almost real time. It performs trace holding, circle half transform, should be an uppercase, sorry, Mr. Half. And then path planning performs tracking and inverse kinematic at 2 Hertz. I don't really need to do too much, as you can see. I don't want you to track me all the time because sometimes it hit me. My hand is red, you know. I'm the red skin. I'm the red skin. Anyway, you see what I meant by I'm red skin. The control system is basically have a lower basic feedback loop performed by the dynamic so it's not, I'm not doing that. It's every joint has its own feedback system. I think it's just PID. Okay, some references before I go into the demo. If you want to know more about this, you can Google keyword forward inverse kinematics for planar manipulator. MIT has an openware course. Not sure whether it's openware or just space. You can look for the robotics class. There's a kinematic lesson in there. It talks about 3 degrees of freedom and a spatial plus 3 degrees of freedom. No orientation. Orientation is really complicated. Usually 16 frames. Anyway, the book I pass around, Richard Paul's book, Robot Manipulator, is another place you can look at some of these equations. Okay. Let's see if the thing's working. Okay, here we have this object that we're tracking here. By the way, I based this software on a piece of code that floating around YouTube and things like that. Just the very basic code that I changed and add a whole bunch of other things to it. So as you can see here, this is the part that we are tracking, and this is the location, X and Y location, and this is the radius that you're seeing. And we're doing a half transform on this thing. Basically, if you try to fit the circle that you see in the image, okay? And then if I extend this image a little bit, you can see the, let me see if I can extend this. You can see the plot. And this is that threshold. So you can turn this around. It's almost every time. Okay. I'm not running the robot at very high speed right now because there's a problem with my power supply. Every time I run at very high speed, or if it hits something, it kind of saturates the motor, and I have to reset the system. So. Okay, so to run this stuff, I basically turn on the robot. Now I turn on the robot, basically it's ready to send command out once you find a place to go. And here, so what it's doing is every time I move the part around, it basically figure out that the disc has moved. And anything on the circle is something it doesn't like. I have to make sure it doesn't go. Now we have a problem. See, once you get into that mode, it desaturates the system, and then that causes a problem. Just so it's and then reset the thing. Unfortunately, that's how it is when you work on a robot. It's a lot of time things just don't work the way designed. There's an API probably, I have to look it up. And
So this is the difference between a robot that's several hundred between many thousands,
I mean,
right?
the time I put in is already probably 60 hours, not every weekend or whatever, you know, daytime when I have the time. So, yeah, see right now, it's not tracking it properly. They have to deal with the same problem we're dealing with. It's just that they hide it behind the scene in the software. It's kind of you buy a piece of software, if you look underneath, there's a lot of things.